Hi, good afternoon, everybody. Thanks for joining us today for our latest webinar. The topic today is metallurgy and metal failure. It's going to be presented by one of our long-term training associates, Dr. Phil Harrison. Just a little bit of background about today's presentation. It will take about 45 minutes, hopefully, for Phil to go through the slides, and that gives us around 15 minutes at the end of the presentation to ask any questions that you might have. If you have any questions, you should be able to see an attendee chat box. Put the questions in there, and I said hopefully we'll get to about 45 minutes and we'll be able to answer as many of those as we possibly can. If you have any technical issues, normally just refreshing the page does work, or checking Wi-Fi, etc. is typically the things that cause issues. But enjoy the presentation, and I'll hand over to Phil.
Good afternoon, everyone. Thank you for joining. Before I start, I'll say, as Dana says, long term, I've actually been a metallurgist now for above 50 years. So I've worked in a number of industries, seen a lot of things, and just explained to Darren, didn't realise how much I have forgotten over the years. So hopefully this is a presentation, something of experience. The reason why I've put a section on metallurgy is people outside the engineering sector quite frequently ask what you do for a living, a career. I say metallurgy, and all of a sudden you see this kind of dull look appear in their eyes. And I wish I had a penny for every time somebody said to me, "Oh, you look at the weather, do you?" So I just thought I'd start off with a little brief introduction of metallurgy from a metallurgist perspective, what we get involved in, what we do, and then just look at metal failure very, very briefly, but then in a little bit more depth, just cover the main cause of engineering failures, just to lead in a little bit, just to see if can, like I said, just do an overall coverage of this rather than obviously go into depth. So could I have the next slide, please, Darren? Right, what is metallurgy? Lots and lots of things. I was told when I first started, it was the study of the science of metals, and obviously reading this out, science and technology of metals. When metals are used as part of a design exercise, obviously everything is designed around the property, a property or a range of properties, which we'll be covering in the next few slides. This property is developed by the structure which is developed in the material. The structure is developed by the processing, how we make this. For example, do we just cast the material? Do we cast it, hot work it? Do we cast it, hot work it, heat treat it? By modifying what we do to a metal, we can modify the structure of the metal. And when we modify the structure of the metal, we alter the property. That's what metallurgy is in one slide. That's all we cover. No matter what we do, we are just trying to engineer materials to give you the structure that you want. Could we have the next slide, please, Darren? So what is it? These are all the little things that we cover in metallurgy. And again, these are just things from my experience. You might get another metallurgist going, "Oh, you do this, this, and this, and this." But casting, whenever we make a metal, we cast it. And people might say it comes from the molten state. We actually alloy the material, create the chemical composition we want at this stage. And you might say, well, we're about powder metallurgy. The majority of powders are actually made from the melt. So lots of things are cast. We can cast a number of different things. We can actually cast through various processes where we have the finished product. For example, pump housings quite frequently are the finished product. Turbocharger housings are the finished product. But castings have limitations. They have limitations on properties. It's a fantastic process for making shapes which are difficult to make by any other technique. I'm not saying impossible to make, but very difficult to make by any other technique. But the major limitation is on the properties. We have to modify the properties. The reason behind this is a cast structure is inherently less dense than a hot work structure. It has porosity in there, micro porosity and macro porosity. By hot working, any unoxidized pores are actually healed up, in essence, densifying the material. So the hot working process, which could be, for example, forging, where we're using a hammer, rolling, where we're actually, well, it says rolling, where it could be rolling bars, could be rolling sheet, could be rolling plate. This heats the metal up. The metal undergoes a process called recrystallization, where the coarse cast structure of the original casting is replaced by a finer grain structure. The forging and rolling further refine the grains in the material, and again densify the material not incredibly, but it is incredible. It's incredibly increasing the properties, or dramatically increasing the properties of these. The properties of a wrought product compared with a cast product, every single property is improved, whether it be proof stress, tensile strength, fatigue life, elongation, fracture toughness. All properties are increased by hot working. Then, when we've done all this work on it to refine the structure and overcome the cast structure, we have to heat treat it. The heat treating can take various different routes. We can use steel, where we do what's called a quench and a temper. It might actually be surface hardening, where we're using something like carbonization of a steel. It might be a solution treating an age process that we do in aluminium alloys, or it might just be a straightforward annealing, where we're removing any built-up stresses in the material. And these stresses can result in problems at a later stage. For example, the stresses can affect fatigue life of materials, can affect corrosion of materials. And then when we've done that, believe it or not, metallurgists look at machining. Quite frequently, there are machining problems with materials. This can come down to various different things we do with them. For example, metals can be treated or heat treated to make them easier to machine. An example, this is spheroidizing annealing of steels, where they are heated to a temperature, held for a long period of time, might be as long as 12 hours, and it creates little shapes in there which facilitate easier machining of the material. We also get involved in testing, whether it be mechanical testing for example, proof stress, yield stress, tensile strength, elongation, etc. Or it could be checking the chemical analysis. We get involved in everything like this. When we go back to mechanical testing, the tensile test is the most carried out test on metals. It is used to verify that the casting, the heat treatment, the mechanical working we've done on the material has been carried out correctly. It is almost just a proof stress that makes sure that everything has worked. Then we get involved in failure analysis. If something's gone wrong with something, quite frequently called in to look at it and just assess what has happened, whether it's just simply looking at a fracture surface or doing a complete analysis of the background of the material, analyze the chemical composition, mechanical properties, looking at the microstructure of the material to make sure that the structure which was described earlier on, to make sure that structure is correct, the structure which was expected. Because if the structure is not expected, quite frequently, this can result in failure of the material. And also get involved in corrosion or prevention of corrosion. Corrosion causes major issues. We have the material which is used mainly throughout the world, which is steel. Above 90% of engineering materials are steels. And if you don't use a steel, the steel is used in production of every other metal that we have. Unfortunately, it corrodes a lot. It's really can almost disappear in front of you. So we get involved in corrosion analysis and also methods of preventing corrosion, whether it just be a basic paint system or it can be cathodic protection, for example, taking it to another level. And also we get involved in material selection. Quite frequently specifications are there which will tell you what you need to order. But if there's an oddball one, can you get something that can fit this criteria? It might be something where the properties are of a certain range, whether we have to have a corrosion resistance, and whether it has to be cheap. So then we can get involved in looking at various materials and then putting them forward. Then there's research and development work, looking at new alloys, looking at new heat treatments, looking at how these can fit into your production facility to make sure that things can be done correctly, and also developing of new materials totally. Obviously, metallurgy, this is slowing down. Over the years, we are doing a lot of work on refinement of what we already have, but research still carries on. And we also look at production routes. These are the casting, forging, rolling, etc., machining, heat treatment. What do we do to get the materials so we have the correct microstructure at the end of the day, which in turn will give you the correct properties? And then troubleshooting. Obviously, with my reaction there, it's my favorite. Working on the shop floor when things go wrong, when you can try and determine what's gone wrong and just say, well, if we do this, we change that, there's a potential for this to happen. And all of a sudden, things can move around very, very quickly, where you can change things where it isn't working to where it is working. Could I have the next slide, please, Darren? Right, metals. Metals are crystalline. They're built on what's called unit cells. The unit cell differs for different materials. There's quite a number of different unit cells or subdivisions, but there are 4 major ones. These define the properties of the materials. What we have in metals as well, we have this defined structure, but also they are formed in layers. And materials can move on these layers. These layers can slide over each other. Sliding over each other gives the potential to have movement in there. And also, if we stop them sliding by doing various things, for example, we put things in the way to make sure it doesn't slide, we can increase the strength of the material. But once again, these structures that we have define properties. For example, there are cubic materials, not very frequently found in metals, face-centered cubic materials, body-centered cubic materials, and hexagonal close-packed materials are the 4 basic cells. Face-centered cubic materials undergo something what's called ductile brittle transition at low temperatures. They can change from being totally ductile and over a few degrees difference turn to brittle materials. Unfortunately, this happens in face-centered cubic materials. Unfortunately, again, steels are face-centered cubic. So we have to actually had to carry out research and development on steels to develop new steels that didn't undergo this transition above room temperature. And by happening above room temperature, it means the materials are brittle above room temperature. And also how these crystals are packed together defines how they deform. Metals have things called slip systems in them. They have slip planes and slip directions where these planes of atoms will glide or slide over each other in specific directions. The more number of slip systems there are, the higher the potential for work in that material. For example, face-centered cubic and body-centered cubic have far more slip systems than hexagonal close-packed, so they do work easier. Could I have next slide, please, Darren? So what properties do we have? We have to control properties. These are the major ones that we look at. These are not really the chemical properties of the material. Obviously, we've not looked at controlling properties to control corrosion, etc. in this bit, but hardness. What is hardness? It's resistance to surface deformation. It's resistance to indentation, resistance to scratching. For example, a hard material will always scratch a softer material, which is one of the very, very basic hardness tests which is carried out, which is historically the oldest hardness test. And then we have the strength of the material. The strength is the ability to bear a load, but the strength falls into a number of different categories. If we have, for example, different forms of deformation in metals. We have what's called elastic and plastic deformation. Elastic deformation is where it's initially loaded. You take off the load at any point in here, in this zone, and the material will return back to its original shape. It goes beyond a point called a yield point. Once it's beyond this yield point, it actually changes in behavior to become what's called plastic deformation. The plastic deformation that we have is permanent deformation of the material. But as you carry on stretching the material, it is a mixture of both plastic and elastic deformation throughout this region. When we could just go a step back to the yield strength, the yield strength is where you start getting, like I said, permanent deformation there. This is what's used for the design of materials. Materials such as steels have defined yield points, which is called the upper and lower yield point in the majority of steels, which is easy to see on a tensile test. Other materials, we do not have this luxury. So we use what's called a proof stress. And the proof stress is calculated from various factors, which is outside the range of what we're talking about now, calculated from various factors it used for the test piece. The most frequently used is what's called the 0.2% proof stress, which basically it's 0.2% of the original, what's called the gauge length, which is this factor I'm not going to describe, 0.2% of the original gauge length, which is a function of the diameter or cross-sectional area of the test piece. And then we've gone beyond this, then the material, obviously we're stretching a material, it's a constant volume. So what happens is it gets thinner and thinner. As it gets thinner and thinner, the load per unit area increases. Then all of a sudden we get to a point where the material cannot stand or withstand any more load and it breaks. That is the break point. Might not be the maximum load the material can take, because quite frequently on ductile materials it isn't. But when it starts necking down, as it's called, the strength per unit, load per unit area goes up and the material will break. And then we have ductility. This is the ability to stretch a material without breaking. This is permanent deformation. This is not elastic deformation. It is plastic deformation. This is measured after the tensile test has been carried out. Ductility and strength are measured using a tensile test where we're working out what the mechanical properties of the material are. There's other ways of measuring ductility, for example, cupping tests and bend tests, etc. But it's accepted that ductility is part of the tensile test. Then we have toughness. Toughness is the resistance to crack propagation. It is not the resistance to crack initiation. A material might already have a crack of some form in it, for example, a machine mark, or it might have been caught by a screwdriver or something. That can be cast as a crack. Toughness is the resistance of the propagation of that crack through the material. A brittle material has zero resistance to crack propagation throughout it. When you have a brittle material, once it starts cracking, the majority of cases, the crack will continue through to destruction of the material or destruction of the test piece or material without any additional loading. Where if you have a material that's tough, you have to keep putting a load into the material to cause failure. And then another property that we look at is creep. Creep can happen at room temperature, but it's mainly classed as an elevated temperature effect. This is where you have loaded a material and it stretches under load, but the load might just be its own load. It might be a long item which is incorrectly braced, and that could actually just load and extend and extend and extend. But it is mainly classed as an elevated temperature process. It occurs as a function, it occurs at elevated temperatures, but it is also a function of the melting point of the material. It becomes significant above about 0.3 of the melting point of the material in degrees absolute. So, for example, the higher the melting point of the material, the better the creep strength at elevated temperatures. And then we have fatigue. Fatigue loading. Fatigue is cyclic loading of materials. It is a very, very, it has been looked at and examined probably more than any other mode of failure in materials. It's been proven to be significant since the early 1820s. So it's been looked at a lot. And as you see, when we talk about fatigue in a little bit more depth later, and you can see why it is very, very significant. Oh, sorry, could I have the next slide, please, Darren? So what do we have that controls properties? A lot of these are all linked together. We have grain size. In metals, you want the finest grain size that you possibly can. When I mentioned earlier about atoms moving through grains, through the crystals, grain boundaries can actually stop the movement and increase the strength of the material. The finer the grain size for a given material, the higher the strength and better ductility within reason. The only case that I know of where coarse grain size or very, very coarse grain size is optimum is in creep, because creep, depending on which model you look at, is a grain boundary effect. And the fewer the grain boundaries, basically, the better the creep resistance. We also have grain orientation. When we work a metal, when we forge it, roll it, extrude it, for example, you give directionality or a fiber to the material. It stretches out and elongates in the direction of working. The properties change according to the direction of the material. When it is elongated and stretched, the longest the direction of working gives you the optimum properties. The properties across the width of, for example, a plate are slightly worse, and the properties through the thickness of the plate are worse still, the so-called Z direction. Quite a few specifications now, and actually on thicker plate, are asking for Z direction testing to give you the worst case scenario. And then in materials, we also have phases. Phases are areas within a material, within a metal, where it has its own crystal structure, its own composition, its own mechanical properties, and a distinct boundary between itself and other phases in there. The combination of how we adjust these phases affects what happens in the material. We can get dispersions of different phases. For example, when I mentioned machinability earlier, we have in steels something called pearlite. It's a mixture of two other phases, which is ferrite, very soft, and iron carbide, which is very hard. By extended heat treatment at just below 700, about 650-ish, the long plates of iron carbide form these balls or round up a bit, and these give you the chip breaks that improve the machinability of the material. So again, by heat treatment to modify the phases in there, we are modifying the properties. We'll go a little bit more on that when we get to heat treatment. We also have inclusions. Inclusions are part of a metal. We don't really want them there in most cases, but we can't help it. There can be anything from bits of slag or bits of refractory that's come through from the furnaces or from the melting process through to mold washers. So lots of different inclusions. So we have to live with them in a lot of cases. And then we have precipitates. Precipitates can come out of materials when it is made, or we can specifically heat treat a material to form these precipitates. And then we have alloying elements. Alloying elements affect a lot of different things. They affect the grain size of the material, they affect the phases in the material, they affect the precipitates that we have, and they affect something also in steel, something called hardenability, which again we'll talk about on heat treatment. But alloying elements also greatly affect corrosion resistance. We have stainless steels. We have a steel which corrodes. If we add above 11.5% chromium to that, we form what's called a stainless steel, and it prevents corrosion of the material. We have various other things, for example, aluminium bronzes. Copper is very corrosion resistant. By adding aluminium to it, you create a product which is very, very corrosion resistant. And then we have the mechanical working. You said when you direction of working that you do, how you extend it. Every time you work a material, where you're hot working a material, you are stretching it, you are refining the grain size. The refinement of grain size is a function of the reduction. A lot of specifications will call for a minimum cross-sectional area reduction of about 3:1, but most places are 5:1. But can you imagine? You have a 300 millimeter thick slab of material that comes down to a 3 millimeter thick piece of plate, which is probably used for making a fridge or something. That is an incredible amount of working. Also, we've only covered hot work, and we have cold working of metals. When you have cold working of metals, what this does is something called, it's strain hardening of the material. The strain hardening increases the mechanical properties at the expense, increases strength and the improved stress, yield strength, etc., at the expense of elongation and toughness. So we then do a process called heat treatment, called annealing, to recover these properties. But every time we heat treat, if we do it correctly on cold wet materials, we refine the grain size. And heat treatment, we have what's called non-heat treatable and heat treatable materials. Heat treatable materials are classed as those which can be hardened by heat treatment. For example, steels, for example, age-hardening aluminium alloys. But every metal can be annealed. Annealing, like I say, recovers properties. What it does is you get things which are too hard, and if you carry on working them, you can break them. By annealing, you recover the properties, take them down soft again. Then we have normalizing, quenching, and tempering, which are in the main for steels. And the strange thing is, normalizing and quenching and full annealing of steels are carried out all at the same temperature. The only difference in this is that with cooling rate, anneal is very, very slow cooled in a furnace. Normalizing is air cooled, and quenching is, as it says, into a quenchant, could be water or oil. When we quench into water or oil with the steel, we form a different phase. The phase is called martensite. It is its own type of phase. In the majority of cases, it is very hard, but very brittle, and we have to have a process of tempering. The tempering is a low temperature heat treatment, which forms precipitation of some carbides out of the martensite and softens it and makes the material more usable. Could I have the next slide, please, Darren? Right, we're now on to with the subject of this was metallurgy and failure. So let's look at different types of failure now. We have straightforward overload failure. This is where we put too much of a load in it, whether it be tension, where it's been stretched too much, where it's been bent too much, where it's been compression, where it's been squeezed too much, where it's torsion, where it's been twisted too much. These are straightforward overload. In a lot of cases, this is part of when something's been designed incorrectly, or something stupid, for lack of a better term, has been done in use of the material where it's been used outside of its design envelope, which has resulted in failure. Then we have impact failure. Generally, tensile failures are slow. They are where we are moving things slowly. Impact, as it says, this is where you hit things quickly. Give them a sudden knock with something. This is also called toughness testing. This is measured using what's called a Sharpie impact test. As I said earlier, the major problem with this is if you have a tough material, it's great. But if you have something that isn't tough, which is brittle, it will fail, could fail at zero or have zero impact strength. This can happen in steels when they undergo ductile brittle transition. Again, well known, and it can be designed out in most cases. We have fatigue life, which we're going to talk about a little bit more later, which is this is cyclic loading. Creep, which we've briefly covered, which can be long-term, can be high temperatures. Once again, it's just extension under load. Creep can happen at room temperatures, but it's a very, very long-term process on most engineering materials, except if you've got something, for example, like lead, which can creep very quickly at room temperature. And corrosion, all different things on corrosion. Corrosion is a very, very, very big subject all on its own. It covers the degradation of a material by its environment. Whether this could be just pure water, it could be an acid, it could be a straightforward erosion corrosion process, but it can fall into several different categories. We have general overall corrosion, mainly when we see steels, when we see a rusted steel, that's general corrosion. We have pitting corrosion. Generally, this happens on materials which are protected by a passive oxide film, for example, stainless steels and aluminium alloys. You get discrete areas being removed, and you get perforation or permeation of things through the thickness of a material without much weight loss or anything. And then we have crevice corrosion. Crevice corrosion happens underneath things. You might, for example, have a washer on a nut or a bolt, and that crevice is formed under something. You do not see it's happening until probably it's too late. Then we have galvanic corrosion, where things are connected together. And the least noble, as it's called, the most negative material on its own electrode potential, corrodes in preference to the other. That can also be used to protect materials, by the way. But we have the general corrosion, pitting corrosion, crevice corrosion. These could all be classed as microgalvanic corrosion cells in the way they behave. Then we have environmentally assisted cracking, stress corrosion cracking, which happens under specific conditions. You have to have a material which is susceptible to a specific corrodant in combination with a stress which is above a threshold level. For example, copper alloys and ammonia. You can just crack as a result of any internal stresses from fabrication of the material or built-up stresses through use of the material can result in failure of these. Then we have hydrogen embrittlement. Hydrogen, very, very small atom, can diffuse into materials and then can push them over the limit and form cracking. For example, on stress corrosion, we might have something where the internal stresses are within a limit. Hydrogen can permeate in there and you can form stress corrosion. This is then called hydrogen-induced stress corrosion cracking. And then we have wear. All different things. These are abrasive, adhesive, fretting wear, etc., where we are rubbing materials away in some way or another. Wear is covered by what's called the science of tribology, which various things are used. For example, different materials against other materials. We have lubrication, we have loading, we have whether or not you have abrasives within something, whether it's liquid contact, we can contact between metals. Lots and lots of different things can happen in there. So lots of different types of failure. And also going back to impact and toughness, we've briefly covered ductile and brittle failure. Ductile and brittle failure look completely different. Ductile failure fails, you have warning of failure when it's going to happen. Things start moving. It is a very dull, fibrous type of fracture. Whereas you have a brittle material, you get no warning. It can break without any deformation around it. So you'll look at something which has got no necking on it, nothing around it, and generally a shiny fracture surface. You could say that is a brittle failure. So could I have the next slide, please? So this is modes of failure. These are some types of failure that's there. You can see fatigue is by far the #1 cause of engineering failures in materials. No matter what industry sector you are in, you can get fatigue failures. Right things from aircraft right through to, for example, nail guns can undergo fatigue on them. Torsion is still high there, but we use a lot of rotating machinery, but also you can get torsional fatigue failure. Then we have stress corrosion cracking, which is well known. We know how to stop it. Tensile failures, like I said earlier, generally that's a part of bad design or use outside the design envelope. And then we have other types of failure, mainly corrosion, wear, etc., which are well documented. So we know all about these things. So obviously, with fatigue being there, we're going to talk about it a little bit more. So could I have the next slide, please, Darren? So these initially looking at overload failures. These are where we've exceeded the yield strength or the tensile strength of a material. This is where we've pulled it, where again, it's gone outside of its design envelope. But the appearance of a fracture surface or the angles and looking at it can tell you what type of failure it is. Obviously, looking at tensile failure, if you have what's called necking, where you've got some reduction in cross-sectional area of the test piece or of the failed component, you can assume that that's ductile failure. If you have no necking of the material and it is a straight line across the material, which is perpendicular to the direction of the stress, that can be assumed to be brittle failure. Then we have torsional failure. Torsion is twisting rather than stretching. If the angle of the fracture is at 45 degrees to the twisting, that is brittle failure in torsion. If the fracture is parallel to the rotation, it is ductile. And then in compression, if the material bulges out, we know it's a ductile material. If it gets cracks down the outside of it, we know it's a brittle material. So just looking at the appearance of a material when it has failed gives you the potential to assess what has gone wrong in it. Could I have the next slide, please, Darren? So again, we'll talk about fatigue a little bit more depth because it is a massive subject that affects every single industrial sector there is and every application there is. It is failure under cyclic loading. The initial fatigue that was noticed was on railway axles back in the 1820s, but it wasn't fully discovered until the 1850s what had happened and what had gone wrong with this. So that is straightforward rotating bending. So what do we have that cycles, that goes up and down? We have car springs, for example. Let's just look at automotive. Car springs, gears in cars. So we have anything that's moving can undergo some form of cyclic loading. The load is generally under the yield strength of the material. Because if the material yields, it will not start cracking. It'll start reducing cross-sectional area, but you will not be building up enough strain energy in the material to actually cause the fatigue crack to extend. Failures will only occur when there's a tensile stress in the material, and never if it's in compression. But quite frequently, if you've got straightforward rotating bending, as in the railway axles, you might be 50% tensile, 50% compressive in the material. The major issue with fatigue is the load cycles which you are using. For example, if you are mainly tensile, for a given amplitude, the fatigue life will be lower than if you are mainly compressive in a material. It is mainly a surface effect. Most cracks start at the surface or slightly subsurface. So the surface condition of the material is of vast importance. It is the guiding factor in fatigue, as you'll see from the next slide when we get there. It is also affected by corrosion in a number of ways. If a material corrodes, it affects the surface. It creates pits and dimples on the surface of the material. This can be the initiation of a crack. Also, you can get corrosion within the crack in corrosive environments, which can accelerate the movement of a fatigue crack through a material, reducing the fatigue life of the component dramatically. And again, depending on which source you look at on this, some sources will say 75% of engineering failures are caused by fatigue. Some places say above 90%. And if you talk to companies who are involved in prevention of fatigue failure, they'll quote things like 95%. But it is a vast subject area. And again, the number of failures that we can have for fatigue can cover everything from aerospace, automotive, biomedical, even things such as household drills and things like this can be covered by fatigue. Could I have the next slide, please, Darren? And this is what some looks like. The fracture can initiate where you get changes in section. A change in section can be, for example, when you see on the crankshaft here, where we change from the journal to the flange. It can be that, depending on what happens in there. Or one of the favorite areas is a screw thread. Absolutely fantastic for fatigue initiation. What happens with it, the fracture will initiate somehow at a surface. And again, if you have something which will amplify a stress, for example, if it is a thread, a change in section, if you have a change in section which is very, very sharp or very, very rounded, can greatly affect the lifetime of the component. Fatigue life is really, you can have up to 90% of the fatigue life can be, or 99% can be taken up just by initiation and growth of materials. Or if you have materials such as welds, for example, which are in essence a surface defect, the initiation section could be completed straight away into a growth of a crack. The fatigue cracks that we see are very, very distinct. They have what's called beach marks on them. And you can see them here in the top. You can see on the left of the diagram there, you can see the lines going through it. The bottom diagram on the left, you can see the lines, the striations going through there. These are the fatigue striations, which you can use to identify or trace back where the fracture started from. Go to the next slide, please, Darren. And these are briefly some others. You can see where the cracks grow. You can distinctly see the striations in the material. You can also see the final failure, which is rough. The final failure in fatigue cracks, to my knowledge, I have to say that because there might be some technical paper somewhere which says against this, but to my knowledge is always ductile failure. The logic behind this is that if you have a material that's not tough, that can undergo brittle failure, once you initiate a fracture, a crack in this, for example, through fatigue, it can actually propagate straight through the material. So you can see on this where the crack is actually initiated from and where it's moved through the material. Next slide, please, Darren. And these are stages. These are where we get microstructural change in the material. This is where we start getting permanent damage. This is where we start getting buildup of stresses in the material. The stresses, very, very briefly, are strain energy built up, the creation of a crack, and the surface area then depletes the strain energy, which then builds up again, the crack extends, etc., etc. And these cracks then become millimeters and then form these dominant cracks, which are striations, which in turn keep moving through and form the beach marks. And then eventually the cross-sectional area of the material is too small to be able to allow one cycle of movement. But the first two stages can be 99% of fatigue life, or if you have something with a deep scratch in the material, or for example a weld, you might have overcome this stage and you might be 50% of the life is occupied by these. Go to the next slide, please, Darren. And this again, I'm sorry for over-egging this, but the very brief slide, you can see here what we started with, having nucleation of the crack on the left-hand side. Very, very small crack. Then it starts moving. Then it gets moved through the material. Then it moves, we have the crystallized stroke, grainy, fibrous fracture at the end of this that you can always see. Quite frequently, you don't always get these nice striations on the surface because obviously it's a failure. Things can start pulling apart and start hitting each other, so they can get leveled off. And again, looking at the nucleation side, you can see there, if we have a surface defect, the nucleation side has been overcome. Next slide, please. So, how does surface condition affect fatigue? You can see here a mirror finish, not a commercial finish. This is a total mirror finish on something, on a material which has been beyond, this mirror finish that's set for reflectors, etc. Beyond what we do for aesthetics is one. You can see as the surface condition gets worse and worse and worse, the factor goes down where we might only have 0.1% of the fatigue life left, or fatigue strength of the material, if the surface is very, very highly corroded. But how do we overcome this problem? Next slide, please, Darren. Sorry, forgot about this one. I'm going to come to problems. If we could have gone to the next slide, please, Darren, because I know we're running out of shorter time now. So how do we reduce fatigue? Basically, remove surface defects and improve design, remove sharp corners and stress raisers. The last slide we looked at is something called intrusions and extrusions. This is a microscopic or microstructural effect on metals during fatigue. And what it means is no matter what you do to set the material, it will get you in the end. And how do we watch its inspection? We can watch crack growth and use fracture mechanics to predict what is happening with materials. For example, in welds, we use correct weld design and reduce the applied stress if needed, or we can change the design of the material, get rid of corrosive conditions so they can basically stop a material from, help initiate a crack on a material. And the best one to me, put a compressive stress in the surface. Next slide, please, Darren. And this is what we can do. Basically, you put a compressive stress in a surface. By hammering them, you get up to 60% of the yield stress as a compressive stress in a surface, depending on what you do. There's various methods of doing this. But, for example, as far as I'm aware, every valve spring on every automotive on Earth is shot peened. The majority of structural components in commercial airliners, on metallic ones obviously, are shot peened. It is not the ultimate method for putting very, very deep compressive stresses in, but it means you can cover large areas very, very quickly. So again, putting compressive stresses in can alter the fatigue life of a component and give it orders of magnitude longer life than it would have otherwise. So next slide, please, Darren, and this is the industries that's affected by fatigue, everything. The reason we've stopped at water transportation is I could not find anything with Z. Obviously, there's something with Z out there, but it affects everything from aerospace right through the whole gamut of every single industry sector there is affected by fatigue. Hence why we concentrate on fatigue, why we look at fatigue, why there's been so much work in minimizing fatigue. Thank you so much for listening, and any questions?
Thank you, Phil.
Thank you.
Yes, we have quite a few questions, which we'll go through as many as we can. So we'll start at the beginning. First question was, how do you tell the difference between low cycle fatigue and ultimate stress failures of quality forged items?
Let me just write this down to be low cycle fatigue and...
Yeah, how do you tell the difference between low cycle fatigue and ultimate stress failures of forged items?
Well, low cycle fatigue, there should be several, if not more, well, quite a few more than that, cycles on a surface. You should be able to see the difference, whereas a straightforward UTS failure, it is just straightforward necking of the material. It should be easy to see from, if you go back also and examine it, to look at what the lifetime or history of the material has been. If you look at the history, if it has not undergone any type of cyclic loading at all, obviously you can turn around and say, well, that cannot be low cycle fatigue. But again, looking around the fracture itself, not looking just at the fracture surface, but looking around it, again, see if there's any necking there, see if any striations on the surface.
Very good. A lot of these questions, as you expect, feel very technical. So when a completed part has been CNC machined from a billet of 6082 T6 aluminium, how do I know the maximum allowable service temperature to avoid change of material properties? Is it the tampering temperature?
Your T6, I've got to flash my mind back to aluminium alloys now. T6 is I'm sorry about this, I've got a fly that's really annoying me at the moment. The T6, that is quench an artificially aged material. So is the question there, when you're actually completing a material and you're CNC machining it, is this where you're scared of heat increase on the surface during machining of this component? Because I would say, again, from my experience, I've never ever come across any problems with this. I can't be more specific on it because there are people who, generally I can speak about aluminium alloys, but not specific alloys in this. But in my experience, I've never come across anything where a CNC machine will affect it, because obviously you've got to heat it up and hold it at what, a couple of 100 degrees on a surface for it to try to overage at all anyway. So to me, I would not think it's causing any issues on it, to me, but again, I could be wrong on that.
Cool. More of a broader question. What about the consideration given to human factors and limitations of the inspection and quality control procedures?
Right, yeah. Quite frequently, if you look at failures or examining failures, my experience has been look at the human factor involved. We do have one of the days where we talk about failures, and I'm not going to go into it in detail on this because I think it's catastrophic what did happen. But humans getting involved in things, or humans who have no technical background or understanding of things, where, for example, you have a beam which has been assessed to be okay with, for example, 1,000 kilograms on it, and somebody thinking 2,000 will be great on that, why not? And it breaks. Something goes wrong with it. We've had a big engineering failure that's been in all the newspapers this last week with the submarine. Massive engineering failure. That will be human factors. Design's gone wrong, or design was absolutely perfect and somebody cut corners, the human factor come into it. How do we engineer it out? By inspection? I think human nature, in the majority of cases, will always try and take a shortcut, if possible, to make things easier for them. Once things have been designed, if they've been inspected correctly, that's as much as an engineer can do. We cannot design in human factors. I'm sorry for keeping saying the word, but like I said, quite a few of the failures I've investigated have been caused by human failure or human errors, which has resulted in not material problems at all. And it is very, very difficult to get the message across that there's nothing wrong with the material at all. It has been caused by a person, and that does seem to cause issues. So I hope I've answered your question there. Sorry, everything is off the hoof here, just trying to cast my very old brain back. So next question.
Yeah, how do you think metal 3D printing will affect the metallurgy field as the process gets cheaper and more widespread?
I first came across this about 25 years ago, and it was going to whitewash every single other type of material fabrication there was. Forget machining, forget alloying, forget this, forget that. And we're still waiting for it. It has its uses. Obviously, it's becoming cheaper and cheaper. I've got to admit, my involvement in this has been mainly on powders, but also on polymers. And some of the polymer things I've seen have been just absolutely unbelievable. My favorite was a nose, which is a prosthetic nose, which had been made for someone in a polymer to match the skin. And I just thought, wow, it was a, obviously a catastrophe for the person, but it is quite strange holding a nose. But on metals, there's too many, to me, there are still too many inherent problems with the process. For example, oxidation in there, porosity in there, can we guarantee strength, and etc. It might go down the route where we do it like we do with castings, for example, where something is made and then the 3D printing does several test pieces from there. And we assume that if the test pieces pass, the material's adequate for use, again, as we do with casting. So I don't know, that might be the way things go in the future.
Thank you. We'll get through as many of these as we can. Is there a reason why fatigue has been the most researched failure mechanism?
Yeah, it's the most common by far. It's caused most issues. If you look at this logically, obviously, like I said, the 1820s, Verla got involved in the 1850s and looked at this and then found out why. The problem continued. Even in the 1900s, there were people from an institute that you work for in London that's still saying something called crystallization was causing failure, still saying that fatigue didn't happen, even though it did. Then it led on to things as it's carried on. For example, 1930s, mentioned car valve springs. It was accidentally found that shot blasting car valve springs, which initially was thought to remove the scale after heat treatment, improved the mechanical properties and life of them. That then was found that it was the compressive stresses in the surface from the shot blasting which caused it. And then we look at things like, we have the Comet failure in the 1950s. The Comet was an incredible aircraft that flew in as the Nimrod for many, many years after. That all of the design had been worked out on maximum lengths of crack, etc., but it still failed. We are always looking to prove, because every single thing that we have, when I mentioned, for example, biomedical, a big cause of failure of quite a number of implants is fatigue failure, believe it or not. So it covers every aspect of human nature. We know how to minimize fatigue, again, due to all the research that's been carried out in it. We know how to minimize fatigue failure by correct design. but we cannot fully eliminate it yet. The only way to actually work with it in most engineering applications is to try to prove a design lifetime. For example, let's look at cars. That crankshaft will last a minimum of 100,000 kilometers, for example. Or if you have a component that's a rotating shaft on a pump, for example, that will last 1,000 hours of use before we need to inspect it. So again, fatigue, it's because it's such a big area, so because it affects every aspect of everything that we have, it's been investigated to the nth degree to try and stop it. Again, it is known how to design in safeguard for fatigue, but again, whether or not it fully stops it one day, I do not know. I think I'm waffling on a bit too much on this one, because I get quite evangelical about fatigue, because it is still one of the subjects that we well know about, that I still think we will never ever get rid of. All we will do is minimize the effect of it. So sorry for waffling on a little bit there.
Yeah, but in danger of further waffling, we have a second question on fatigue, which is fatigue only a consideration when cyclic loads exceed the metal's proof strength?
It's below the proof stress. Basically, the loads are below. If you get it above the proof stress, you are actually plastically deforming the material. When you plastically deform it, you're removing the strain energy in the material. The buildup of strain energy is responsible for initiating the crack. For example, let's look at cracks. Strain energy in surfaces. Hatfield rail crash many years ago. It's all common knowledge about this, so there's nothing secret coming out. That's something called rolling contact fatigue. This is where you get hertzian pressures subsurface below the yield strength of the material, which build up to a point and a crack will initiate. I always say this, I'm sorry about this, I always say this because I cannot remember it ever in metric. It's about 7th thou below the surface of most materials. You get this crack form below there. If that material, if you'd exceeded the yield strength of the material on that, it would have plastically deformed, and you would not have built strain energy up to a level there where you could have initiated a crack. So it is always below the yield point of the material.
Okay, I think we've got time for one last question. This is quite a topical one on a couple of points. But first of all, are new alloys still an area of active research, or does the industry feel that steel is as good as it can be? Could AI be used to be more easily, cheaply predict the effects of different alloying elements?
I would say yes, new alloys are always being investigated. There's little things. Going back historically, we've had 20 years, 25 years of duplex steels, but those were invented in the 1940s. And the reason that we didn't make them or couldn't make them, we didn't have the manufacturing routes to make them. Now, so we're investigating not just new alloys, but manufacturing processes, how to make things, how to melt things better, how to refine how we make it. But yes, new alloys are always being investigated. The amount of research is minimal in the UK compared to what it used to be quite a few years ago with the closure of various labs. Yes, I think AI has its uses all over, and I think it could do a lot of, I'll not say shortcutting, I'll say speeding up of processing for looking at new materials. So yes, I think it could be really beneficial on how we get new materials formed. Whether or not it's going to happen fairly quickly, or whether it could take 20 years to machine learn to do this, I do not know. But yes, I think it could be of use.
Excellent. Yeah, I think we'll have to call it a day there, folks. I think we have another question might dip over the 1 hour mark. Just first of all, say a big thank you. The feedback on the chat's been incredibly positive. We've had hundreds of people attend. There's probably another 20 questions we could have gone through. Finally, I just want to give a bit of a plug to Phil and the courses that we run, which you could probably see on your screen there. So we have public courses running throughout the year on all the topics you can see on your screen. We also can run these in company, whereby if you have more than, say, 4 or 5 people at any organization, we can do in-company training as well. Also, on the topic of AI, that's actually, Phil, that's a topic we just started doing some training on ourselves as well. So,
all right.
Yeah, quite interesting to see your thoughts on that perhaps at another time. But I think finally just give a virtual round of applause for the presentation. As I said, the feedback's been fantastic. I apologise if we couldn't get through all the questions today, but thanks for attending. The presentation is recorded, copies will be sent, and also it will be on our YouTube channel along with all the previous webinars we've done over the past few years. They're available there as well. I would say the website again is a great source of information and resource for any information on training courses as well. But finally, a big thank you for attending, a big final thanks to Phil for the great presentation, and have a good weekend.
Thank you for attending, everyone. Thank you.